So today we're going to finish up section 13.3. So we're going to start off by talking about what it means to have two events that are considered to be independent or dependent. So if we have two different events that are taking place and we look at the probability of the second event given the first event, so the conditional probability, if that equals the probability of the second event, then those two events are considered to be independent of each other. However, if that conditional probability does not equal the probability of the second event, then those two events are dependent of each other. So we're going to go through a few examples of looking at pairs of events and how mathematically we can go through and figure out if they are independent or dependent of each other. Okay, so the first example we have tells us that we have a penny and a nickel that are being flipped. And so event A is that it's going to be tails on, that should say tails on the penny. And then event B is that it's going to be heads on the nickel. So we know event A is that we're going to have tails for the penny, and event B is that we're going to have heads on the nickel. So the very first thing that we need to do is we need to figure out the probability of each event independently, separately. So we said A is that we're going to have tails on the penny. B is that we're going to have heads on the nickel. So when we think about the likelihood of that happening, we know that when we flip a coin, whether it's a penny or a nickel, the only two outcomes are that that coin lands on heads or that coin lands on tails. So the probability of event A happening, which is the penny landing on tails, that would be 1/2. The probability of the nickel landing on heads is also going to be 1/2. Now we need to look at calculating that conditional probability. So the probability of B given A, and if we look back at what we did earlier in the section, remember our formula for calculating this. The numerator is the probability of the intersection, and then the denominator is the probability of whichever event is after the given. So for this one, it's going to be the probability of A with the way I've set it up. Okay. So we need to figure out the intersection here. And so when we're figuring out the probability of the intersection, we really want to think about the sample space here. All of the possible outcomes from flipping these two coins. So because we are flipping two coins, if we think about our sample space, both coins could land on heads. The first coin could land on heads and the second one could land on tails. The first one could land on tails and the second one could land on heads, or they could both land on tails. So when we're looking at the probability of the intersection, what is the probability that we have the penny land on tails and the nickel land on heads? We notice our sample space has 4 possible outcomes, and there's only one of those 4 outcomes that satisfies both conditions. So the probability of the intersection would be the one occurrence out of the 4 possible outcomes. So when we substitute in to look at simplifying this, we have the intersection, which is 1/4, over the probability of the penny landing on tails, which is event A. So we have 1/4 divided by 1/2. And so now we just want to simplify this. So we're going to simplify, we're dividing fractions. So remember, in order to do that, we are going to keep the numerator. We're going to change our operation to multiplication, and we're going to take the reciprocal of the denominator. And so after we simplify this, we get 2/4, which is equivalent to 1/2. So we've gone through and calculated the conditional probability. So what we need to do now is just remember what it means for two events to be independent. So if they are going to be independent, we are comparing the probability that we just calculated to the probability of that second event, which is in front of our conditional sign. So we go back and say, what was the probability of event B? In this case, it was 1/2. And so we notice these two probabilities are the same. So because they are the same, that means the two events we started with are considered to be independent of each other. So we would say, since the conditional probability, the probability of B given A, equals the probability of B, the events are independent. So if we look at the next one, we're dealing with a deck of cards. So we're told a card is drawn randomly from a standard 52 card deck. Event A is that the card is red. Event B is that the card is a face card. So if we think about the probability of drawing a red card, we know there are 52 cards in our deck. We have our 4 suits, our hearts and diamonds, which are the red cards, our clubs and spades, which are the black cards. So there are 26 out of the 52 that are red, so that's the probability of drawing that red card for event A. The probability of drawing the face card for event B, okay, we've talked about this in class. The only face cards you have in the deck are the king, the queen, and the jack. So there are 3 cards in all 4 suits, so that gives us 12 out of 52. And so then we need to think about the probability of the intersection. So if we think again about the set, well, we could have our king of hearts, we could have our queen of hearts, our jack of hearts, our king of diamonds, our queen of diamonds, and the jack of diamonds. So we can see there are 6 cards that fall into both categories. So that would be the intersection. So the probability for the intersection is going to be 6 out of 52. So we set this up. The probability of the face card, given that it was red, the numerator we said is the probability of the intersection over the probability of that event listed behind the conditional, the vertical bar. So we substitute in, we found the intersection was 6 over 52. And then we are dividing by the probability of red, which is 26 over 52. And so simplifying here with keep, change, flip. So we keep the numerator. We change it to multiplication. And we take the reciprocal of the denominator. And then when we look at multiplying, the 52s will cancel out. They'll divide out at the end. That would leave us with 6 over 26. And so what we are searching for is we want to know what is the probability of event F. So the probability of event F, we said, is 12 over 52. But if we take a couple of minutes and compare these two, 12 over 52 can be reduced down to 6 over 26. So we're comparing these two probabilities, to see if they're equivalent, because that's what's going to determine if they're independent or not. So again, since the probability, the conditional probability of F given R is equal to the probability of F, the events are independent. So the last one we have of this type says we have 2 dice, one red and one green are rolled. We're told event A is that the total is greater than 7. Event B is that the green die shows a 3. So when we look at the probability of event A, so what we would need to do here would be to think about the fact that we're rolling 2 die. Each die is 6-sided. So we've talked about the fact that collectively, when we think about how many possible outcomes are in the sample space, there are 36 different outcomes that you could have when you roll 2 dice. If we go through and we were to list them all out, which we're not going to, but if we wanted to, list all of them out so that we could figure out how many times will the 2 dice add up to be bigger than 7, we would find there are 15 instances out of the 36 possible outcomes where that happens. Now, the second event is that the green die is going to be on 3. So regardless of what the roll is for the red die, the green one is established, it's set in stone of being at 3. So because of that, there are 6 instances where that will happen out of the 36. And so we are going to want to think about the sample space for the intersection. So for the intersection, if we want a roll that satisfies both of these conditions of it being greater than 7, but also the green die being on 3, that means the red die would have to land on 5, and the green die we said is stuck on 3, or the red die lands on 6 and the green die is stuck on 3. Those are the only 2 instances where a roll from those dice is going to satisfy both conditions. So that is our intersection. So there are 2 out of the 36 instances that satisfy both. And so now we want to look at the probability of the or the conditional probability of B given A is equal to the probability of the intersection over the probability of that event that's behind the conditional A. So we substitute. We said the intersection is 2 over 36 divided by event A, which is 15 over 36. And so then we do our keep, change, flip. So we keep the fraction in the numerator. We change our operation to multiplication, and we take the reciprocal of the fraction in the denominator. When we simplify, the 36's will divide out, and that's going to leave us with 2 over 15. So we said we were comparing this to the probability of event B, which is 6 over 36. And so when we compare those two, even if we were to simplify 6 over 36, that simplifies to 1/6. 2 over 15 is as simplified as it's going to get. So we notice these do not equal each other. So in this instance, since that conditional probability does not equal the probability of B, the events are dependent. So that takes us through instances with figuring out if two events are independent or dependent of each other. We have a few other types of problems in this section that we're going to look at. The next couple of examples are requiring us to look at our conditional probabilities, and so we're going to do that using our table. So according to the US government statistics, mono is 4 times more common for college students than the rest of the population. Blood tests for the disease are not always 100% accurate. So we have a table here that summarized information they've collected on various students, from whether the blood test was positive or negative and whether or not the student actually has mono or not. So for part A, it says if a student is selected from a group, find the probability that a student has mono given that the test is negative. So we're looking for the probability of mono given that negative test result. So when we set this up for our fraction, we're starting with that first event. So in this scenario, mono is event B, testing negative is event A. So what we're looking at is we have all of these 72 students. We are thinking about event A is how many students tested negative all together. That's our starting point. We're narrowing down this group of 72 and putting our focus just on the ones that tested negative by their blood test. So that's going to be our denominator. It's the total number of negative. Now the numerator is how many students with the intersection fall into both of those categories. How many have mono and tested negative by their blood test. So we start with the denominator, how many tested negative. So if we look, we can see there were 30 students altogether that tested negative for mono. And we can also see, if we go down and look at how many have mono, 18 of those fell in the overlap region. So 18 out of 30. And so we can calculate this either by simplifying the fraction or getting the equivalent decimal. And if we get the equivalent decimal, we're going to find the probability is 0.6. Okay, the second one we have says a student is selected. We're looking for the probability that the student does not have mono given that the test was negative. So again, we're looking at they tested positive first, that's event A, and then from there we're focused on how many don't have mono. So no mono given positive. So with this one, the very first thing we're doing is out of the entire group of students that were tested, we're focusing on how many of them tested positive. So when we look at that, there were 42 of them that tested positive. So that's our denominator. Because we said it's total positive in the denominator, and then no mono and positive in the numerator. So 42 tested positive. And then how many did not have mono? Well, that's the overlap. So 17 of those 42 did not have mono. And that decimal, we're going to do an approximation here because it's not exact like it was in part A. So it's approximately 0.405. Okay, last two examples we have. Example 12 says, assume a softball player has a 0.62 probability of getting a hit in each bat. Assume the player bats 4 times. What is the probability that she gets a hit only on her first at bat? Okay. So we want to use the information we're given. So we need to know what is the probability that she actually hits the ball when she gets up to bat. Well, that's given. That is our 0.62. Now we also need to think about the fact that she's going up to bat 4 times, and she's only going to hit the ball 1 of those 4 times. So we need to think about what is the probability she does not hit the ball. So we need the complement. And so if we remember, the probability of an event and the probability of the complement of the event always add up to equal 1. So we can use that. We do 1 minus the probability she hits the ball, and then that gives us the probability that she misses the ball, which would be 0.38. So if we're looking at the probability that 1 out of 4 times she hits the ball, we can think about our counting methods like we did back in chapter 12. So we have 4 events that are happening. We're multiplying them together. And we said the first time she gets up to bat, she's actually going to hit the ball. So the first time, the probability she hits it is the 0.62. But all of the other 3 instances, she does not hit. So that's the 0.38. So we're multiplying all of these together to find the probability that this sequence of events actually happens. And so when we calculate that, the decimal we're going to get is 0.0340. And the last one we have in this section says a person wants to purchase a DVD drive for his laptop. Assume 56% of the drivers are made outside the US. If the US made drivers are 4% defective, and those that are not made in the US or foreign made are 7% defective. Determine the probability that the drive purchased is US made and is not defective. So we're looking for an intersection here because we're looking at the fact that it's made in the US and it's not defective. So we go back and we use that formula for calculating the intersection, which is the probability, the conditional probability, so the probability that it's not defective, given that it was made in the US, times the probability that it was made in the US. So if we think about the fact that we need, for the conditional probability, the probability that it was not defective given it was made in the US. So we are thinking about how many of those made in the US were defective. Well, that would be 4%. So if we want the probability that it was made in the US and it's not defective, if only 4% of those made in the US are defective, that means the other 96% made here in the US are not defective. So it'd be 0.96. And we're multiplying that by the probability of those made in the US. So we're told 56% of those are made outside of the US. So if 56% are made outside of the US, that means the remaining 44% are made in the US. So we multiply those probabilities together and we get 0.4224. So that wraps up chapter 13.